You good? Okay, so guys, here's the situation. Welcome to my studio. Let's get this set up. The situation is this. We have an image. I don't care what image it is, just whatever, what's your whistle. And if we were to take that and just scale that up, the issue we're gonna have is, regardless of whether or not it's seamless, it is going to tile. If we want to texture something, we need a texture that just works no matter how much you scale it by. Now the question is, how do we do that? And I want you to think like this. We're gonna take our image and isolate a single section. I don't care what section it is, it's like a random sample. I'm gonna do that, and then I'm gonna take a second sample. If we can now combine these in a way where one extends the other, we're gonna be set. But of course the issue is, there's an obvious seam. If we kind of do a 50% transparency, they still have this weird overlap. And it turns out the way we do this is we calculate the difference between these images. We're gonna call that a difference or a energy map. And if we now find the minimum path from top to bottom, like the lowest energy, lowest difference path, we've created a scene. We have the left tile, we have the right tile, and we have the two kind of separators. Now this is great because if you see here, if we do this process again and again and again and again, we're basically building our image. That's called texture synthesis, and it lets us take any image and just make it as big as we want. So please enter my realm. Like literally bring the camera in.
This video is sponsored by Brilliant. More about that later. Before we do a Blender implementation, I just want to give you a free tool that does it for you, and then we'll go into the theory. So this is like a famous paper that came out that explains the image quilting idea. There's a person who seemingly 6 years ago implemented it into some code, and I compiled it into a executable, just an exe file that does it for you. For example, if I have an image like this, which happens to be very, very small, all we need is the sample image and then the quilter exe. I'm going to open command prompt, take it, you drag it, in other words saying, I'm using this executable, and then for the rest of it, I made kind of like a demo of what you would type in. So I'm going to copy this here, and the way you want to think about this is we are synthesizing a certain image. In this case, that's going to be the sample image. Replace our image right here, and then the rest of the settings you can keep the way they are. Hit enter. So as you can see here, we synthesized more image without doing the whole seamless thing, and you can keep extending it. In other words, you can like take that new image, put it in the program, or if you just want to like triple the resolution instead, you do -S, that's for size, and then you type in 3 or 4. But now I want to talk about how to do this in Blender, for example. Here's a nice image I like that we want to extend, which would be hard to do normally because the tiling would make it very evident. I'll call it tile.jpg. And what we're going to do is we're going to follow the 3 steps of the paper at this point. So remember, we kind of extract samples of the image, ideally the best fitting ones, and then we overlap them and try to find the best kind of cutting curve, which can be seen as kind of like the minimum energy curve or the shortest path. Let's start off with whatever, a cube. Make that a geonodes, and we don't need the original object. I'm just going to add a grid. So right now this is kind of like 2 by 2 pixels. And then if we add a parameter for the resolution, as I increase this, now we have like a 200 by 200 resolution image. I'm going to bring in a image texture node, which will tell us what image do I want to bring in. That is going to be the tile image. You're seeing that it is there, but there's this obvious tiling, which again is the issue, right? If I was to make this higher resolution, you can see horrible tiling. So we want to make sure that this is mapped onto the grid using UV space, not world coordinates. So it should go from 0 to 1 on both the X and Y axis. Well, luckily for us, the grid comes with such a UV map. So connect that there, and now we have the image as it was when we downloaded it. Now the next step is we need to make a little function that samples parts of the image. So maybe this one, this one. The important thing is that it's random. You can either do this by isolating some geometry and deleting the rest, or much simpler, we just kind of zoom in the image and move it a little. I can take the UV map and kind of like shift it along. I'm going to start by zooming in with the scale, which you can see does this essentially. So if I set this to 0.5, it's going to be, well, I guess a quarter of the image in terms of area. So I'm going to sample, let's say 20% of the image, which apparently has a watermark, but we'll work with it. I don't care. And then we are going to add a random offset. So I'm going to add a random value as a vector. I only care about the X and Y component. So let's say you can go from 0, 0 to, I don't know. I mean, you could do the math. I'm just going to do it to like 0.7. when I plug this in, we get a mess, and that's because it's picking a random value for every single point that's offsetting on a per pixel level, instead of picking just one random number. To do this, you take not the seed, which will vary this, but the ID, and you make the ID all the same. So you just plug in a number like 0 or something. And now when I do this, I'm sampling different parts of the image very easily. This can be our pixel grid, this can be our resolution, constant ID, scaling, translation. Let's take everything we have here, except for the resolution, which I want as a parameter, Control G, and now we have this as a group, which I'll call sample. And really the only other thing I want control over is let's make the seed something that is exposed. So I'm going to put that right there. And now thanks to that, we can grab a random sample just with this group at a certain resolution, which we'll call 200 by 200. So let's start off by taking 2 random samples. Again, ideally we pick the best fit one, so you try a bunch of them. But for now, let's pick 2 random samples. So the first one can be a seed of 0, and the other one can be a seed of 1. And I need them to overlap. So we're going to have one image here, and maybe the other one kind of here, where this kind of distance, this number of pixels that it overlaps, is the kind of overlap value. That's a horrible O that we care about. Take the geometry and join it. And for the bottom one, I'm just going to shift it over a bit. I'm even going to move this like upwards so we can see the overlap a bit better. What I want to do at this point is isolate this overlap, and that's where we're going to find our seam. So this is going to be kind of a weird way to isolate it, but just follow along. Make sure one is on top of the other, and I'm going to take this bottom plane and do a bunch of ray casts. So I'm going to shoot upwards. And the ones that hit the plane, I keep. That is the intersection, whereas one over here hits nothing. Ray cast onto the second sample, and I care about, is it a hit or is it not? And I want to take the sample right here, separate geometry by what is and isn't a hit, and make sure that the ray direction is facing upwards on the z-axis, and that we have the transformation. And when we do that, we get this isolated section that, of course, is dependent on how much overlap we want. A second thing we can do is we can actually extract the attribute. So not just isolating the intersection, but for that section, we sample what the color or the texture even was. We want not a float, but the color, and let's plug this in right here. So in other words, I have more information than what is the intersection. I also have the attribute, which was the texture above. Also, I have the original color. So this is from the kind of the first tile over here. And then I also have this one, which are going to be different, assuming we have random samples. And I care about the difference between these. How bad is the overlap? I can do that by taking the distance. If you think of colors as kind of like vectors, as 3-dimensional quantities, red, green, blue, I take the distance between the 2 colors. So this is kind of our difference map. That, as we kind of translate our sample, will look different. So you can think of this as points that are very white. The difference is really big. The overlap's horrible. Like, they don't look like each other. Whereas kind of sections that are black, like this contour over here or over here, they tend to be more similar because the distance, how different they are, is very, very tiny. And ideally, the seam, which normally would just be kind of cutting this in half, ideally, we kind of do something like this, where we find a path that kind of I don't know the word. It hides the seam, essentially. And the beauty of that is it is basically the path that is most black, lowest difference, and that is a node we have, shortest edge path. And then for that, we need to make a selection, for example. So I am going to do, what is it called? Edge path to selection. You connect this next vertex index into the next vertex index, and then we basically have to say what points are we starting at and what points are we ending at. In this case, I want to start anywhere on the top and end anywhere on the bottom, and just kind of find the curve of best fit. So I can look at the position vertically on the y-axis. So let's separate the y component, which looks like this. I care about when the value is equal to 1 or 0.5, whatever it is, and then -1 or -0.5. Take the y, find where it is greater than a certain number. So that gives us this kind of gradient. And it seems like the number should be 0.5, and if not, like 0.4999. Conversely, we take this, we flip it to say when it's less than 0.4, or I guess -0.4999. I guess I could say greater than or equal to 0.5, and then less than or equal to -0.5, and that way we don't need to do any weirdness. So I have my top, I have my bottom, as in all good relationships. And this is what I want to find the shortest edge paths of. Say this is the end and this is the beginning. And let's kind of see what that gives us. So I'm going to take this geometry and view the shortest edge paths, which by default will give us kind of nothing, right? Because all the edge paths are basically the same. There's no difference between them. We want to say the edge cost, in other words, which edge is bigger or smaller than another. That is going to be defined by this difference map. We take this, we say this is the edge cost, which will tell us what route is good, what route is bad. And now when I view the selection here, you can see it gives us us kind of these paths, which if we set this to, I think it's point, now we get solid paths. Now the issue is it gives us multiple, we can work with that, but you can see we have a path kind of like defined over here, so I'm going to draw this out, and let's compare that to the difference map. You can kind of tell that makes sense. It goes along this black contour. This video is sponsored by, drumroll, even though you already know, Brilliant, the place to learn useful and technical skills using hands-on kinds of, digitally hands-on lessons. Learn anything from math to programming to statistics, where every single module isn't just like watch this video, but you're solving puzzles, you're answering questions. You do not progress until you know that you've understood what was already taught. And for this tutorial, a module I can recommend is geometric thinking, which isn't just a random choice, right? Obviously geometry is important for 3D, but what you're going to see is there's actually a section about tiles and tessellation, which of course is relevant to a video about generating tiles, but I think it's like an interesting natural extension. So you can check that out and everything else Brilliant has to offer by using this link below, and there should be a QR code. And this is good for a 30-day free trial of Brilliant, along with, if you want to take it further, 20% off a annual membership. So that is what's up. So maybe I want to keep the best one. The most obvious thing for me is instead of the selection, we can take edge paths to curves, which will essentially kind of give us the same thing. So I connect this here, connect this here. But this time we say, what is the source geometry? Which will look like this. It gives us the same thing, but now they're actual curves or geometry or whatever you want to call them, that when I trim them, you can see that these are kind of different paths, different branches. And I want to find the one that is the best of these, although all of them are fine, but I want to find the best of these. I can do that by taking these curves and sorting them by a certain metric. So I'm going to sort elements, which is a way to say which curve is better than another. I'm going to say, look at the curves, in other words, the splines. And then we need to say, what is the kind of the metric that we're using here? I'm just going to do what makes the most sense to me, which is saying which curve is the shortest here. We'll keep the one that isn't like a crazy seam. Maybe you do want it, but easy for this example. So I'm going to find the length of every curve, which isn't that. Maybe it's the spline length. This will give us the length of every spline. I'm going to put that as the sort weight. And now you can't really see it, but we've reorganized things so that the one with the minimum length is going to be index 0, the next one's going to be index 1, and then the longest one is going to be like index 10 or whatever. I can separate out the curve, and I care about which one is index 0, in other words, the shortest, the lowest total length. So let's see where the index is equal to 0. And it turns out to be this curve. Just to show that the sorting matters, if I was to take the reciprocal, in other words, saying kind of the reverse of it, 1 over big is smaller than 1 over small. So we've reversed the relationship. And when we do that, we get a different curve. So you can either pick the longest, the shortest, or any metric that you want. Maybe you want the one that's closest to the center of this kind of overlap. This curve I want to define as kind of the cutting thing of our overlap. Again, I want to remind you all of this is procedural in the sense that I can change my overlap, I can change my seed, and just kind of get different results here. So I think we can just take all of this, everything we just did, Control G to make it a group, which we can call like select curve or, whatever you want to call it. So to review, we have like 2 different samples that we then use ray casting to find the overlap and the attribute that it had and whatever. And then based on the difference map, whatever that may be, which will change depending on the seed and all this, I'm going to pick the curve of minimum energy or whatever it is you want to call it. So I guess what we can do is turn this into a selection. So I'm going to take this curve and turn it into a mesh, which is useful because now this is a bunch of points that perfectly line up with our pixel grid. And what I want to do with this is I want to take our overlap and kind of find the proximity to this selection curve thing. So let's find the closest points, which by default looks like this. You can see it's highlighting our path exactly. And I care about where this distance is, let's say less than 0, less than 0.01. Make sure it's like 0.0001, because that should perfectly isolate this because the pixels line up. So there is a distance of 0 sometimes. And I think that should do it for us, because if we now take our geometry and we split the edges, in other words, saying if we have this curve, I want a left and a right section, I'm going to split the curves based on this selection. We should now have 2 different islands. We can check this by doing a scale elements, and let's see what this gives us. It gives us nothing, because maybe we need to find the closest edge or something. So this divided our thing, in this case, into 3 segments, and I believe that's just because this curve happened to touch this. So maybe our metric should be which one was closest to the middle or whatever. But I'm just going to change the seed until that isn't the case for an example. So let's say we have this one. And now when we scale elements, we have a very clear left and right portion. So if I've kind of like one sample here and then another one overlapping it, I want to keep this section and this section kind of like a Venn diagram. And then for the section on the left, I keep one island and then the other one gets the other island. We divvy it up in half. Well, I guess this is why we didn't only make the selection based on the raycast, but also the inverse of it. So we kind of have what's remaining of the left side. And I want to join that with, this island over here. So how do I separate left from right? Well, these are different, literally islands. They're not connected to each other because we split edges. So I can now separate again the geometry by where the mesh island, which we'll have two of, so index 0 and index 1, I believe. Let's take where the island index is equal to 0. And that is going to be this section, and the inverse is going to be the other section. So I'm going to take the inverse, and I am going to join that with this selection. So this is our left chunk. And if you see a bit of a gap here, that is because when we separated our overlap and our non-overlap, we separated by points, which means if they have a common edge, that's going to be an issue. Take this and make it separated by faces. For the other side now, I'm going to join the inverted section, and then whatever was over here, which we could calculate, or we can take the original sample over here, which is the other one, and we can just kind of move it down a bit so that it is beneath the rest of these, which will have one section be underneath, but when we have a top view, it will kind of obfuscate that. Now, the last thing that's going to be an issue is we didn't really save these parameters, right? They shifted in kind of like this weird way. So it might be easiest to just kind of store this information. So in other words, I'm going to take this color, which we evaluated, and then for each sample, I'm going to store that data as a color, care about this color, and I'll call this like the value. And that should propagate along the rest here. Just to be safe, I'm going to make sure the attribute we're using over here, I'm just going to replace this with our value so that everything is nice and consistent. Same thing kind of over here. We have the same issue. So I'm going to use this same attribute. Now, when we join everything and view it, you're going to see it's almost like we didn't do anything. We still have this very clear seam here, even though we have kind of like separated it by portion. And the reason for that is basically this section over here needs to inherit the other color, if that makes sense. Right now, they're both inheriting from the left sample, whereas the whole point of the dividing line is this left one gets information from here, and the right one gets information from here. To do that, I'm going to isolate the right segment, which is the issue, and I need to overwrite this kind of value we made, which is a color. I need to overwrite it in a way that it inherits information from the right sample. So we're going to do another raycast. I care about this bottom geometry, which again is the second sample. I'm going to shoot this array downwards. That's fine. And the information I want to carry over is the attribute that we so-called value. And that should be stored right here. That way you can see when we do and don't store this, we get kind of different things. So just to keep it super simple, I join one island, I join the other island, I join the inverse of the overlap, so basically the left side, and then I'm going to join the right side. Okay, moment of truth. We now view this and boom, you can see we now have two tiles. We have a left tile and we have a right tile, which together, if I was to join them, do not overlap in any way. They just don't. Forget about it. They don't. But this thing we made has a very clean overlap. It's actually quite hard to find where the seam is. So this is the minimum energy, in other words, best looking seam we could find. And I think 200 was actually quite low. So let's bump up the resolution to 500. And that just changes the path a little. And at this point, to kind of play around with this, you can change your metric. You can do all kinds of things. Like a lot of people use something that's called the L2 norm. What that means is you just take the distance and you take it to the power of 2. So this is without, this is with, and arguably it should be better because it basically penalizes any distance that's really bad, and ones that are really good, it says they are good. If you have a graph over here that describes kind of like the error or the difference between them, when it's a power of 1, we get this kind of linear relationship. The worse it is, it just kind of grows linearly. But when we do a power of 2, you get a curve like this, which says the ones over here are really good. They're a low kind of cost, and the ones up here are actually quite different. Another obvious one is where is it sharpest and most blurry? Because where it's sharpest, maybe that's where you put the seam, whereas blurry, there's not much you can do there. And I want to really say, as we change the seed, we're going to keep getting different extensions that have a perfect seam. Like these all look like they well, except for that one, they all look like they perfectly overlap, at least based on this error function. The idea here is you have this thing that takes an image and lets you overlap another, and then you keep doing it. You say add one here, and then you go vertically, and you create this image that is in a sense different than the original because we're just sampling. You could even rotate and do all these kinds of things. But as for step 2, which we didn't do, like we extract samples, we find the minimum energy kind of seam. Step 2 is we don't just kind of pick a random like overlap and just kind of keep it. We actually try them all out and do what we just did, but keep the one that minimizes the minimum seam. So we're getting the best of the best. So it's kind of a natural extension. That more so matters, not for a case like this, but for a case where your sample is like blueberries, where there's very clearly defined shapes. In fact, bro, this is procedural AF. So let's take the same image for both of these. I want to do a wood texture, something that would tile very poorly, but has detail so we can extract the curve. So let's do a wood texture. Inside of here, I'm going to look for this, and it is pretty dang seamless, especially when you consider the original alternative is something with a pretty clear seam line. We replace it with ours, and all of a sudden it kind of just melts away. Here's kind of a complicated one. Let's try that. It has all these lines baked in that would really make it an issue if you just didn't do it intelligently. This is the original. You can see a crazy seam over here. It just kind of cuts off, whereas ours has a much nicer kind of fade. In fact, this is the best example because it has already a predefined line. What about this one over here? Another marble-like texture. This one's great. So this is the original, just a horrible seam, and here's ours. It just kind of blends away. This is the thing. Like, even if you were to make it a seamless texture, you'd have an issue where it would start repeating, whereas this one wouldn't have it because it keeps sampling randomly. So again, original, horrible seam, and ours. It's just massaged away. Okay, so I'm going to clean up this blend file. You can have it if, you know, you're a cgmatter.com subscriber. All project files going back a long time. This one included, so check the description. And yeah, I hope you learned something. Also check out the tool that somebody else made, but I made it an exe if you want the fast approach. But this one's procedural. It works very fast, and you could even optimize it. So thank you for watching. The secret of seamless textures has been revealed.